So let's start. So today we will start universal gravitation. Universal gravitation. What is universal gravitation? Basically, this is the dynamics of planets. Yes, big planets: Earth, Moon, Sun, etc., and the other planets. So basically, there is a Newton's law of universal gravitation. Newton's law, you know, from dynamics: first law, second law, third law. Also, there is a Newton's law for universal gravitations. So Newton says that there is a force between any two objects. So let's draw our first object, mass m1, and the mass m2. And Newton says that there is a force between these two objects. No matter what mass, what distance, they will feel each other. And he says that this force depends on both masses and the distance between these two objects. And of course, as usual, there should be a constant, universal gravitational constant. We have this kind of equation. So as you see, between any two objects. So x is the distance between these two objects from center, of course. They will attract each other. This is the direction of this force, F and F. G is the universal constant and equal to 6.67 10 to the power of minus 11. Mass m1, m2, mass in kilograms, x is the distance in meters. So by using this equation, you can find any force between any two objects. So, but in real life on this earth, why we don't feel this force? So why we don't feel this force? Let's prove it, why we don't feel this force. So let me find this universal gravitational force, or force between me and between the table, which is 1 meter away from me. Force between me and the force between the table, which is approximately 1 meter away from me. In real life, at the moment, I don't feel this force. Let's prove why I don't feel this force. So this is me, and this is my table. My mass m1, mass of the table m2, distance between us approximately 1 meter. We attract each other. Yes, we attract each other. So let's find this force. Let's find this force. F equal to G constant, mass of table, and the distance square. Constant 6.67 10 to the power of 11. What is my mass? Approximately 70 kilogram, for example. Mass of the table, let's say 10 kilogram. Distance between us 1 meter, 1 square. So let's calculate this one. 667 times 7, basically 47, approximately, roughly 47. 10 to the power of minus 9 Newton. Yes, so what does this number mean? What does this number mean? So let's write it in terms of kilogram. Yes, in terms of kilogram. Let's convert it into kilogram. So we need to divide by G, gravity, which is 10. So we will, this force is equivalent to the 47 10 to the power of minus 10 kilogram. Yes, in kilograms. Let's write it in gram. It will be 10 to the power of minus 7 gram. Let's write it in terms of milligram. 47 10 to the power of minus 4 milligram. Yes. So it means 0.00447 milligrams, or we can say approximately 0.005 milligrams. How many times smaller than milligram? 1000, yes, approximately, or 1200. 1 over 0.005, it's 200 times smaller than 1 milligram. 200 times smaller than 1 milligram. We even, in real life, we even don't feel gram, yes? 1 gram, we don't feel 1 gram, 10 gram. It's very small, we don't feel it. This is a smaller than milligram. So that's why we don't feel this force in daily life, let's say. But when it comes to big masses, let's say Earth and the Sun, Moon and the Earth, yes, we cannot ignore this force because of mass. Mass is huge, very big numbers. So that's why we don't use it in real life, in daily life. So let us study the rotation, the motion of Moon or motion of Earth around Sun or Earth. So Sun and the Moon, not Moon, Earth. We know that there is a force between these two planets. Gravitational force. Since Sun is very big compared to the Earth, we will assume that it will not feel this force because it's very big. So that's why Earth rotates around the Sun. Yes, actually, they both rotate around each other, around common center mass. Center mass is very close to the Sun because mass is very big, as Sun's mass. So we'll ignore it. We'll assume that Sun is stationary. Earth is rotating around the Sun. And there is this is a distance between Sun and the Earth, and this distance we call it radius, yes, because of orbit. Earth is orbiting around the Sun, and distance between these two planets equal to radius of this orbit. So this is basically circular motion. Circular motion. If you pay attention to the Earth, there is a gravitational force, direction to the Sun, circular motion, and that's why we have a centripetal acceleration, yes? So according to the Newton's second law, we know that this force should be equal to ma. What kind of force we have here? Universal gravitational force, mass of the Sun, mass of the Earth, r square. Mass of the Earth and centripetal acceleration of the Earth. Mass of the Earth, we can cancel it as you see. So centripetal acceleration equal to constant, universal constant mass of the Sun divided by radius square. So we have this kind of equation. So basically, by using this equation, we can find the velocity or period of the Earth. So we know that centripetal acceleration equal to velocity squared divided by radius. Yes. So this is the velocity, direction of velocity. Yes. Velocity of the Earth. So as you see, velocity of the Earth around Sun actually equal to what? Square root constant mass of the Sun divided by radius. So let's find this velocity. 6.67 times to the power of minus 11. We can quickly Google and find mass of the Sun. Let's do it. Let me find it. Mass of the Sun. Mass of Sun. Mass of the Sun, it's approximately 2 10 to the power of 30 kilogram. Now radius, this is what I got from Google. Distance Sun and the Earth. Distance between Sun and the Earth 150 million, it means 6 zeros, kilometer. We need to write in meters, so it's 9. It's 9. So from here, what we will get? So let me write in this way. Let me write here 10 to the power of 10. So power 10. Here we have power 20. Power 20. Here minus 11, 19. Yes. So 667 times 2 divided by 15, 10 to the power of 9. 9. So from here, approximately velocity equal to, just 1 second. Square root. Approximately 3, 10 to the power of 4 meters per second. So in kilometers, it's a 30 kilometer per second. So 30 kilometer per second. 30 kilometer in 1 second. So this is the velocity of the Earth around the Sun. And we know that we are moving, we are on the Earth, and our velocity also actually equal to this one. We are not stationary at the moment, yes? We are not stationary, we are stationary according to the Earth, compared to the Earth. But for someone who is watching us from outside of the Earth, we are moving with the velocity of the Earth, and this velocity is very big velocity, yes, 30 kilometers per second. So in this way, you can find velocity of the planets. So as you see, there is nothing new. Only you need to know force between two objects. Let's say, yes, force between two planets. Now we know how to find velocity, and we know period. What is a period? Period is a time needed for planet, for object to orbit one complete circle, yes, to do one complete circle. So this is not new equation. We know that length of the circle 2pr divided by velocity, and we know that this velocity equal to what? Square root gmr. So from here we have this kind of equation. We can find any planet's period by using this equation. And again, this equation is not new. You know it from the circular motion. You know this equation. This is not new. So in this way, you can solve universal gravitation problems. So let's see what kind of problems we can do. We can solve. I have this kind of problem. I will read it carefully. Just listen. Using the known radius of the Earth and that gravity, small gravity 9.8 at the Earth's surface, find average density of the Earth. So question is, find the average density of the Earth. So what we know small g, 9.8, we know the radius of the Earth, 6400 kilometers, yes? Centimeter per second square. By using these informations, we should find density of the Earth, average, of course. So first of all, let me explain about this small gravity that we use this in daily life. So before solving this example, let me explain what is a 9.8. This is basically is coming from universal gravitation law. This is the Earth. This is me. This is a building, my house. This is my car, for example. Yes. Why we are on the Earth's surface? Because something is keeping us. That's why we cannot escape the Earth. And this something is actually force between me and Earth. This is Earth, center is here. This is my mass m1, this is my house's mass, this is my car's mass. Yes, we all feel this force. This Earth, our Earth is attracting us. F1, F2, F3. What is the distance between all these three objects and Earth? This is the radius of the Earth. Yes, this is the distance between me and the Earth, Earth's center, of course, between my house and the Earth's center, etc. So F1 actually equal to constant Earth's mass, my mass, distance between us. Force 2, force between Earth and my house, for example, yes, my flat. Only difference is we need to change mass of the object. Because Earth is common for me and for my car. Distance for me and for my car is also common, same. And this is a force between Earth and my car. So as you see, this part is common for everyone. This part is common for everyone, even for you. If we are on the same planet, it means we can just once calculate this part. Because these are the very inconvenient numbers, yes, very big numbers. Of course, I don't want to do these calculations each time. So why not to do it once and keep it, and let's give a name, and that's all. Next time we will multiply this constant number, yes, like this. Why not to do it? So this k actually we call it g, small g, which is 9.8. You understand the reason? Gravity 9.8. 9.8. So basically, small g is equal to what? Universal constant, mass of the Earth, divided by radius square. So let's prove it quickly. 6, 6, 7, 10 minus 11. What is the mass of the Earth? Mass of the Earth. So we'll Google it quickly. Mass Earth. Approximately 6, 10 to the power of 24. Radius, 6.4, 10 to the power of 6, yes? In meters, of course. So if we calculate this one, 6 times 6, 67, 10 to the power of 13, divided by here, 6.4 square. 6.4 square equal to 41 approximately. Here, 12. 12, so it's 6 times 67 divided by 41. 0.97, 0.976, 10 to the power of 1. So as you see, 9.76 approximately, we have a 9.8. Approximately, we have a 9.8. So that's why this is coming from universal gravity law, as you see. Okay, let's continue. We know what is a small g. Now we need to find the density of the Earth's average. So first, what is the density? Density is mass divided by volume. Mass divided by volume. Mass divided by volume. Of course, here we cannot use data from the Google. Yes, we need to use small g. We need to use radius. This is what is given. So mass. The shape of the Earth is approximately spherical. Yes. So let's use this equation. Now let's come to small g. What is a small g? Constant times mass divided by r square, if you remember. So let me multiply both sides by r. G r m r cube. So as you see, we can use this part. Yes. So from here, just mass mass divided by radius cube equal to small gravity divided by gr. Yes. So let's take it and let's substitute it into this equation. So gravity divided by 4 3p g radius. So this is actually density. Well, let's write in this way: 3 gravity 4 pgr. So in this way we can estimate the density of the Earth. Gravity is given, radius is given, others are constant numbers. 3 times 9.8 divided by 4, 3.14, 667 times the power of minus 11. The radius 6.4 times the power of 6. Yes, in meters, of course. So from here we approximately we have this 5.5 times to the power of 3 kilogram meter cube. It means 5,500 kilograms per meter cube. This is the density of the Earth in averages. In 1 meter cube we have 5 tons of mass approximately in average. So this is how you can solve problems. Let's continue. So we know what is a small g. Actually, small g gravity is coming from the universal gravitational law. Universal gravitational law. We know how to find the velocity of the planet around. So calculate the mass of the sun, but okay. So if you remember, we used some data from the internet, yes, from the Google, and the Google says that mass of the sun equal to approximately to 9.9 10 to the power of 30 kilogram. Why not to prove this one? Can we prove by our calculations? We know that period of the Earth around the sun is 1 year. Yes. So period is given. Distance, I think we can find distances. Distance between sun and Earth is equal to 1.5 approximately 10 to the power of 11 meter. 11 meter. By using these informations, let's prove that mass of sun is approximately 2 to the power of 30. Let's do it quickly. We know that gmr square equal to m centripetal acceleration, which is this one, yes? This one. So mass cancelled, mass of the Earth, one of the radius cancelled. gmr equal to v square. So be careful. I'm not advising you to memorize all equations. Just you should. It's enough to know this equation. Is further, it's just coming from the circular motion. So we know the velocity of the Earth, and this velocity of the Earth actually equal to what? The circumference, the length of the circle orbit divided by period square. So from here, gm radius equal to 4p square r square t square. So as you see, mass equal to 4p square r cubed divided by g t square. So now this is equation. So now let's substitute numbers, datas, and let's see. For 3.14 square, radius is given 1.5 times power of 11 cube divided by 667 times power of minus 11. Period we need to write in seconds, of course. International standard SI unit. 1 year is approximately 365 days. In 1 day we have 24 hours, 60 minutes, 60 seconds. 60 square. So from here we can find that answer will be approximately 1.9 times power of 30 So in this case, in this way, we can find mass of planets.